Good afternoon to all of you. So,
Sir.
Good afternoon, 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 sir.
yes, so presenting my screen. So, as I told you, I will be taking test on Saturday. आपका कितने बजे? आप 9 से 10 ठीक रहेगा? 9 to 10 मॉर्निंग.
सर सर
हाँ जी.
एमसीक्यू होगा
8:15 से
सर एमसीक्यू होगा ऑब्जेक्टिव होगा
MCQ होगा.
ओके सर
ये कभी MCQ दे दो, उसके बाद फिर वो वाला भी रहेगा, सब्जेक्टिव वाला नेक्स्ट.
ओके सर
So, okay. Yeah, so we are going to start the new type of thing, and the second part of the bonding, that is ionic bonding. And so this is what we already know. We have discussed the covalent part. Covalent bonding has been discussed, and we are now moving to this part, ionic. So what we have learned so far, covalent bonding, you have seen that when the difference in electronegativity is much, the stabilization achieved would be less. Okay, when this is what you have learned in covalent bonding while making a MO diagram. So if you have equal contribution from A and B, both having orbitals undergoing overlap is like this, then this is the situation. You have very good stabilization. So this is the kind of thing that you already know. Okay. Suppose if the A and B have a huge electronegativity difference, if they have some difference in electronegativity, then you plot it like this. And the stabilization, sorry. In this case, when there is energy mismatch between A and B, the energy lowering will be, it will be to a less extent. Okay, overlap is poor, and you can expect it to be a small stabilization, something like this. So this is the bonding, less stabilized. So stabilization, the decrease in energy in this bonding orbital that you see is less. And so if I extrapolate it further such that there is a huge difference between the electronegativity, then even the stabilization that you can see, plotted with dotted line, it will be even less. It will be almost like similar to, only a little bit less than. So B is here more electronegative than A, and what in the covalent bonding framework, the MOT framework that we are looking at it from that point of view, the stabilization is very, very small. Del E factor is so small that it has almost the same character. The orbitals, this bonding orbital that we are visualizing here, it is having almost the same character as the B atom. And this one should not be stable. Very less stabilization, less stabilized, highly stabilized, less stabilization, less stabilized, and insignificant you do not see any stabilization, almost the energy level. So if this had one electron and this was having one electron and both appeared, then it will be lying over here. So it is almost like that when the bond is formed, the two electrons are almost lying in an orbital which is almost on B. It has the character of the B and not of A. Very less contribution from A and most of the contribution from B. So 95 to 98% it is B type. So this is what happens when you consider. So this by this particular scheme, which is the covalent bonding scheme, if you look at it in this A and B type thing where electronegativity difference is large, when A and B have high electronegativity difference, a large difference, this is the case of large difference in electronegativity. When there is large difference in electronegativity, then the stabilization that you see from this diagram is very, very less, negligible. So it is so less that it is almost negligible. The orbital, the bonding orbital that is formed, it is being this, you see dropping from the energy level of this, it is very small drop, decrease in energy, so negligible decrease in energy, negligible stabilization, that is how we can put it. Stabilization, that is. So in this kind of scheme, if A and B, if they are having large electronegative difference, they do not form a stable compound. But this kind of compound are known to be stable. So if an example of this is that this Na and BCl is more electronegative, sodium Cl. This is a situation when you encounter with sodium and chloride, sodium and chlorine, Na and Cl, two atoms when combined together. If you work out this MO diagram for them, both Na has one electron and it has also one electron. So chlorine has also one unpaired electron p. So if the orbitals overlap, you can think of formation of an orbital, molecular orbital, bonding molecular orbital, which is just having almost the same character as that of chlorine. The stabilization achieved in this way is very, very less, and it should not be much stable. NaCl, so formed from this point of view, should not be much stable. But practically we see that NaCl is very, very stable. So definitely this model of bonding is not able to explain the stability of NaCl. And that's why, so something from this point of view, NaCl not expected to be stable, to be a stable compound, right? So this is the covalent bonding scheme that we are following, and from that, when we construct MO diagram for combining two, we try to combine sodium with chlorine and try to see what is the stabilization. There's nothing like that. So there's something missing. The stability in practical sense that we see in HCl is huge. It is a salt that everybody uses in their daily food. It is a stable thing. So that part is what we are going to, what we are missing here is that the bonding scheme has to be understood in different way, and that is ionic model of bonding. So we have not yet considered that. So we'll just try to learn about this, what it involves. So you can, in ionic bonding, you have one of the electron is highly, as I told you, there is high electronegativity difference between the two. Taking example of that, so you have if one is sodium, one of them gives out electron and the other one accepts electron. So you have NaCl being formed, Na plus and Cl. So sodium atom gives out electron, Cl atom gains electron, and in this way you have a one you have complete transfer of the charge that is taking place. Na plus and Cl minus is being formed, two cations and anions. And then if you have 1 mole of such atoms, they can organize themselves in a regular pattern, 3-dimensional pattern. So each such that one Na plus is surrounded by 6 Cl minus, and each Cl minus is surrounded by 6 Na plus. So this kind of arrangement leads to a very, if you sum up all the forces of attraction, repulsion, of course there will be some, then the overall thing is that there is lowering of energy in this model, which is you have to take into electrostatic model of, just like you have in physics you have studied about electrostatics. So in a similar way, here it is not just one charge, there's number of one cation surrounded by 6 Cl minus, so attraction from 6 Cl minus. In the screen you see only 4 because the 2 is lying above, 1 is lying, one other Cl minus is. So look at this. This is Na plus surrounded by here 4 Cl minus, and 1 Cl minus is above the plane of the screen and behind the screen. So in this manner you have each Na plus is surrounded by 6 Cl minus, each Cl minus is surrounded by 6 Na plus. And that, when you calculate the overall summation of forces, the electrostatic interaction, it gives you net release of energy. So that is the energy of the system is lowered because of the strong electrostatic interactions, and that is we know as ionic bond. So it is always like existing like this in a solid state, solid like things. So it is a very common thing to observe. It is this. But before I move forward, I will just take some. You should also be aware of the properties of these ionic compounds. The compound such as sodium and chlorine, which is जो यहाँ पे बन रहा है. What are the features of those compounds? So a typical ionic compound will so what are the features, main features of, let me just add one more slide to put it differently. So let me take a blank slide, then I can add a few more points. So if I am talking about the main properties of ionic compounds which are formed in this manner, features of ionic compounds. So number one, they are do not conduct. They are mostly crystalline solids. And they do not conduct. So these are things that you first revise, and then with the latest things we'll discuss as we start from the scratch. So they do not conduct electricity in solid state. If you take a crystal of NaCl, apply electric field, you connect it to the two poles of batteries, it will not conduct electricity. हेलो, हाँ गुड आफ्टरनून, क्लास ले रहे थे हम, ठीक है बाद में करते हैं. So what the thing is that, so they do not conduct electricity, this you know, because why they do not conduct electricity in a solid state? Because it is solid, you have arrangement of cations, anions, which are fixed, occupying fixed lattice sites. They are more massive, held tightly in the 3D network. So the electric field that it is not able, they are not displaced from that simple application of a when you apply electric field from a battery, the ions are massive, they are tightly held by each other's in the network that I told you, that 1 Na plus surrounded by 6 Cl minus. So there is no movement of this Na plus or Cl minus when you apply current to a crystal. Okay, so there is no conduction. But number two, you note that when dissolved in water, they do conduct electricity if dissolved. So first thing is that they readily dissolve in water. And this solution, this now conducts electricity. So do you understand this? What is this dissolution, Na plus Cl minus dissolving in water? Why it readily dissolves in water? What is, can you visualize this thing? What is happening? Why it is, if you have more polar solvent, it will be easy to dissolve. So what is the effect here? What is, if I ask you, explain the dissolution of NaCl in water, why it dissolves, why and how, why it dissolves. Then what do you say? So you have positive charges, negative charges, which are attracting each other. So you have to overcome, to separate it, you must separate them first. You require energy. So why it is so easily, the moment you put NaCl salt in water, it dissolves. ये तो 11 से लेके BSc में भी पढ़ा ही होगा आप लोगों ने, बताइए.
सोडियम आयन जो है वो हाइड्रेटेड रहता है, H2O मॉलिक्यूल से घिर जाता है, इसलिए वो सॉल्युबल हो जाता है.
There are two things that you have to consider. So just understand it this way. So
Positive part of water attract negative part of NaCl.
हाँ, लेट मी, सो ठीक है, अब थोड़ा सा और अच्छे से हम लोग समझने की कोशिश करते हैं. सो जैसे कि आप एक चीज आपने देखा होगा, अगर हम चार्ज को इसमें रखते हैं, दो चीजें कंसिडर करनी है पहले, कि Na प्लस, सो इफ यू हैव Na प्लस and Cl minus, suppose separated by, suppose just a moment, for a moment, if they are separated by distance r in vacuum, and the same Na plus and Cl minus this is in water. When you place, so interaction between two things in water. So simple looking at electrostatic. So the force, it has been found that force here, electrostatic force, that is force in water, in vacuum, and there will be electrostatic force acting between them, that will be also in water. So what do you expect? So simple electrostatics tells you that it is Q1 Q2 by 4 pi epsilon naught. So you can distance is r square. So this epsilon is the permittivity in vacuum. So electric lines of forces, how easily it can travel. So that is the best possible manner in which it can travel in vacuum. When the same thing is put in water, this permittivity is reduced, and what we have is that the force in water will be reduced, and you have epsilon, which is represented epsilon. So this is the permittivity in vacuum and the permittivity in. So the force, it has practically, when you do it, if this situation 2, this force is more, the attractive force in the vacuum is more large. This is large force, this is small force in comparison to this. This is something further expressed as Q1 to 4 pi epsilon into epsilon r, that is, we call it as 1 by r square. So this is something. So this epsilon r is the what we know as relative permittivity, and एक मिनट इसी को आप अगर रेशियो ले लें तो इसी से हो जाएगा. So this ratio of two forces, so the force is reduced. Practically what happens, vacuum से water में जब force लाते हैं तो एक तो attractive force कम हो गया, Na plus Cl minus, and this reduction in the force is what we know as relative permittivity. If vacuum by F in water, if you take the ratio, it is turns out to be what? Epsilon if water is epsilon naught. So this ratio will come out to be, so थोड़ा सा जगह कम पड़ रहा है यहाँ पे. सो वैक्यूम ये जो है, और इसी रेशियो को फिर हम एप्सिलॉन आर से डिनोट करते हैं, विच इज अबाउट 80 times. So this is around 76 to 80 times ऐसा कुछ आता है. So the force is weakened. So आपका जो force of attraction है वो 80 times कम हो गया है. Number one. So it is now easier to pull them apart. It is easier to separate the two ions. Just focusing at two ions, we can say like that. So first point is the dielectric constant. This is relative permittivity or the dielectric constant, which you say, which is a ratio of the two forces. So if you have to calculate it, this is the way that is done. So this is what we call as relative permittivity or permittivity, that is something or you can also call it dielectric constant. So this is, so the force in vacuum is about 80 times smaller in case of water. It is less attractive. The force between attractive force between Na plus Cl minus 80 times less. So reduction in force 1 due to the dielectric constant. The medium has a different permittivity of the electric lines of forces. Permittivity is the word that is coming from permission or something like that. How the electric lines of, how easily the electric lines of forces can travel through a medium. So in vacuum, when there is nothing, it is blank space, nothing in there, you have maximum permittivity that is possible. But when you have some molecule, something coming between, so different molecules behave differently. So in water molecules, that is considerably reduced. The electric lines of forces are less easily allowed to travel, to move through, and that way you can visualize that permittivity is different. Now the forces are, so overall result is here. The force in water is, so attractive force is reduced, force F, and because of that, ये तो already बता दिया आपको. So this is one part of the reason why it dissolves. So it becomes easier to separate them out. Now, if you consider them, so this is the energy that is required. You can imagine it's a three-dimensional network, and you have Na plus surrounded by Cl minus. So you will be having all of them and then make it water. So now, so you can imagine you have like positive arrangement of ions like this, Na plus Cl minus. So if you can imagine this way, Na plus, so या फिर उसमें जो पिक्चर अभी आपने देखा, so suppose we have arrangement like this, it will be easier here to understand. I may just rub it off, and so this is the case, and put it here. So now if I start from here, so this is a crystal arrangement, okay, Na plus Cl minus, and when we put water in it, another thing that will happen, so when we have water all around, now we know the force has reduced, attractive force, so it will be easier to take them away. In addition to that, what you have been saying, the water molecules arrange themselves around it in such a way that overall forces so you know water is a dipole. Water has, so you have negative end of the dipole will pointing towards the positive ion, and there is a large number of such thing that molecules, solvent molecules will be arranged. So this visualization has to come. So this is of course we have a limitation of drawing, but there is much more number of large number, like around 10 to 20, around 20 water molecules per sodium or something like that. So there is large number of ions which surround one Na plus ion, and they surround in such a way that the negative end of the dipole, water is a if we are viewing water as a dipole having partial negative charge on oxygen and partial positive charge on hydrogen, then the negative end of the dipole will be pointing towards Na plus, And the summation, so similar thing you can think of happening for Cl minus. Cl minus will be also surrounded by a large number of, so if we can think of Cl minus getting surrounded by water molecules. So you have positive, so positive this time the because it is a negatively charged ion, so negative end of the dipole, positive end of the dipole will be pointing towards the Cl minus, positive end of the dipole. So you can think of something like this: a large number of water molecules like this. So what is this? There is ion dipole interaction. One ion surrounded by a large number of dipoles, and there's huge. This is, and they arrange themselves in such a way. Dipoles are arranging themselves in such a way that the overall attraction is maximized. So summation of these forces. So this is ion dipole interactions. Okay, so this ion dipole interaction is with this Na plus, Cl minus with water molecules surrounding the Na plus, Cl minus surrounded by a large number of water molecules, and in this manner this leads to summation of these interactions will lead to release of energy, and this energy, this is what we call as hydration energy. Hydration energy. So this is hydration energy, or the energy released, and these are called hydrated ions. These are hydrated ions. Hydrated ions. This is also hydrated ion. This is cation and ion. So whenever you, so these are, or in general, if the solvent is something else, you call it solvated ions, solvated cation, solvation energy. So that is a general term we define for anything when solute-solvent interaction happens. One solute, one fundamental unit that constitutes this solute is getting surrounded by large number of solvent molecules. So, and in this particular case, it is the ion Na plus surrounded by large number of water molecules, such that negative end of the dipole point toward Na plus. Similarly, one Cl minus getting surrounded by large number of water molecules, such that the positive end of the dipole, when water is in what the dipole in water that we are talking about, is pointing towards Cl minus. So this is a happy situation. It's a good situation leading to overall attraction. There is a release of energy, which is hydration energy. So both these factors taken together. So in this case, you had the lattice energy that you have calculated when the Na plus surrounded by 6 Cl minus Cl minus. So in a tightly packed manner in three-dimensional networks. So this amount of energy, lattice energy, the energy in this particular case, this amount of energy will be required to overcome and separate them out. You have already reduced that requirement by putting in water, because the electric lines of forces have different permittivity and the force of attraction is reduced. Now secondly, as soon as these water molecules surround each one of these water Cl minus or Na plus, the ion dipole interaction, there is a large number of ion dipole interaction that happens, and the summation of all these interactions is such that a huge amount of energy is released, and that release in energy the hydration energy is much more than the lattice energy, and so it dissolves. And so when this happens, you are not able to see any crystal. It is all transparent water-like solution unless you test it. So this is so basic. So what it comes out to be that the force is reduced, and then there is some amount of energy released when they are getting solvated, and the hydration energy is greater, much greater than the lattice energy. Lattice energy is the energy required in this particular case to break that lattice, to separate each one of them to infinite distance, and each Na plus separated from Cl minus, and so dissolution occurs. So whenever you have to write a solvated molecule, when you write this thing Na plus, जब भी आप इसको लिखते हैं, so when Na plus aqueous, or when you write Cl minus aqueous, what does this mean? This means these are solvated ion or hydrated ion. You call it hydrated ion, and the picture that comes to your mind, that one. So this again the same picture that I had drawn earlier. So a lot of surrounded by large number of water molecules. So that is how you should visualize it. So that is the meaning of when you write reactions or anything in water, you always put in bracket Na plus Cl minus to indicate that the physical state of the ion, that it is solvated, surrounded by a large number of water molecules. This is in short denoted by this thing. So number one, so these are the things. So you also have observed that they are brittle, crystalline. They are hard but brittle. So usually you find that you apply pressure, they are not breaking, nothing happens. But once you exceed a certain amount of force, you apply a certain amount of pressure, वो चूर चूर हो जाता है. It breaks into pieces, multiple pieces. That is brittleness. चूर चूर हो जाना जो कहते हैं ना कि एकदम फाइन पार्टिकल्स में बन के बड़ा सा क्रिस्टल टूट जाता है, उसको ब्रिटल कहते हैं. सो ब्रिटल क्यों होता है? Why ionic crystals are brittle? These are basic things which before we move forward, you should know the basic features as seen. So that also you can where is yeah, so the basic feature that I've just explained to you, when we are talking about ionic solids, they have high melting and boiling points. They're soluble in polar solvents, and this is the coding. You see, hydrated ions. So Cl minus. So the red one is, the green one is Cl minus. So it is the solid state shown in the at this bottom. It is in solid state, which is shown. And here what we are seeing, it is surrounded by water molecules. So you can see the small circle, white one, that is hydrogen atoms. So surrounded by water molecules. Here it is Na plus surrounded by water molecules. So orientation of water molecule is different. And this is what we call as hydrated ions. And the scheme that I have just told you, I think that what I have told you was better than this diagram indicates. So soluble in polar solvents. Why it is soluble? The reason I have told you. One, reduction in the force of attraction, electrostatic force. And then second point is the hydration, which is basically, you have to visualize it as ion dipole interactions. A large number of ion dipole interactions, summation of which gives you overall release of energy, which is much larger than the energy required to break up the lattice. Okay? And the second property, brittle. Why they are brittle? Because you can see it like this. They are arranged in this manner. So suppose you are applying force along, when you apply pressure, suppose the force is applied along this layer. So this layer will be slightly displaced towards this direction. So see, the new situation will be like this. Now see, positive in contact with positive, negative in contact with negative, and then there's a huge repulsion happening and it will just fly away. You are, and it is just only one two-dimensional view that we are having. In a three-dimensional crystal, you can imagine there will be multiple layers in which this kind of interaction will happen, and so it will be this will, the increased repulsion fractures, it leads to total fracture of the crystal that is there. So that, and that's why it breaks when the stress is applied at after a certain point. So you will so beyond a certain threshold value of the force, if the ions are displaced with that force in one layer, then it leads to huge repulsion between all the surrounding layers. And because of the charge, two like charges are coming in contact, positive with positive, negative charge coming in contact with negative ions. And so in this manner, it will lead to huge repulsion and then breaks. So the brittleness of this is also explained. So now we come back to this point, why, okay, so how this ionic bond is formed. Transfer of electrons, so lithium, scheme of lithium fluoride, that is how you can show. Lithium atom giving electron, fluorine atom accepting it, give it, so Li and F plus. So this is one atom of Li, one atom of fluorine. So you have resulting into one ion, one thing. Now, if you have a large number of such, say 1 mole, so you have 10 to the power 23 atoms of lithium, 10 to the power 23 atoms of fluorine, then they will combine together. So because of mutual attraction between positive and negative charges, they will start arranging themselves in a regular manner, and that will be what we say a lattice, a solid three-dimensional network is formed, which is in which regular arrangement of these ions is there. That is called lattice. So you have ionization energy, electron affinity coming into picture. But you know what, there's also one point of consideration here. We have shown that electron is lost. So ionization energy, a positive term. You need to give energy to the system to take away that electron. Electron affinity represents a negative term, that is the fluorine, when it accepts electron, some energy will be released, but that energy released is less. If you actually see the values, energy released when a fluorine atom accepts electron is much less than compared to the ionization energy. Then how does this happen? So the answer is lattice energy. When you're viewing them, one electron, one atom of lithium, one atom of fluorine as in isolation, then you have energy requirement which is not sufficient enough to make that happen. The energy consideration makes it like, but if you have a large number of such atoms together, and then you if they start arranging in themselves in a regular arrangement, that is typically a solid like happens in the solid, then a large amount of energy is released when such 3D network is formed, and that is lattice energy formation. So that is it is the lattice energy which is the driving force of this thing, because otherwise simple consideration of electron affinity and ionization energy is not tells you that it is not feasible for the compound to be formed. But when we arrange themselves in a three-dimensional network, the lattice energy comes in picture, and in this process, arrangement of positive and negative ions in this form leads to release of energy, that is lattice energy. And this is what you have. You find it exists. It exists and it is stable. Okay, and this is what keeps them together, and that's why they are hard and high melting points. And it is because of this that they are held together tightly and do not move when electric field is applied. Only when it is molten or dissolved in water or any other polar solvent, you find the flow of ions is possible. So conduction, it is also to be noted that the conduction of electricity in an ionic compound is through flow of ions, which is more massive than, it is having more mass than electrons. So of course it will be much less in as compared to electronic conduction of electricity. And it is something called Born-Haber cycle, that uh, which is based on the Hess's law of continuous summation. Hess's law of summation. So this is again, it is application. Hess's law itself is an application of conservation of energy. Conservation of energy and energy. So it tells you that whether if starting point and finishing point is the same, doesn't matter how many steps you take, you perform the thing is in one step or two steps or multiple steps, the overall energy released will be same. So that is basically conservation of energy. And when Hess's law was to evaluate this lattice energy, so lattice energy is something that we are talking about is you have 1 mole of like here we have taken example of Li plus, and so if you have 1 mole of Li plus in gaseous state and 1 mole of fluoride in gaseous state, and then they together form LiF in solid. So 1 mole of this giving you this crystalline solid. So this is what you, so this delta H is, so this is what enthalpy, this enthalpy represents the lattice energy. So this energy released in this process, so this is how you have to consider. Imagine you have created the ions, 1 mole of lithium plus ion, 1 mole of fluoride ions, and now they start coming together and a 3D arrangement is formed, regular arrangement, which is crystalline solid. So the energy released in this process is lattice energy. So let's try to understand it in this way. So this is the this is the visualization how it happens. So suppose if you have start from this, lithium in elemental state is solid, fluorine in elemental state, in naturally you will find it is in gaseous form. So this is here, and then imagine it to be occurring. So first step, if you start from native state of lithium, you need to convert it into gaseous state. Why? Because you know ionization energy involved. How do you define the ionization energy? ionization energy is defined as when a gaseous atom is, you take away one electron from a gaseous atom in isolated state, that is the energy, ionization energy, and you define it in 1 mole of such lithium atoms. For 1 mole of lithium atoms, when you try to take away, so that kilojoule per mole, we define it in that way. So if the way you have defined ionization energy, if you are talking about removal of one electron from gaseous state, to first convert it into gaseous state. So this step is the, what we call it, sublimation. This is your sublimation, solid to gaseous state sublimation, or you can first let me put it like that. So that is delta enthalpy of sublimation. The second step you now have is that you have also defined fluorine, the electron affinity. Electron affinity has been defined as the, when a atom, gaseous atom, so fluorine exists in as a molecule, so you need to dissociate it. So this is the F, gaseous atom. So you have a gaseous atom of lithium, gaseous atom of fluorine, and now you give some energy to take away that electron, and lithium plus is formed in gaseous state. Fluorine atom in gaseous state, it will accept one electron and some amount of energy is released. So that is shown over here. Remember, as I told you, electron affinity is always less than the energy required. To ionization energy is more than the electron affinity. So up to this, overall thing is still positive energy. You have, the process is endothermic up to this. Now onwards, when you are looking at lithium plus and fluorine gaseous state, they are trying to coming together each other, and they organize themselves and form this kind of crystal is formed. This is the representation of lithium F solid, lithium fluoride. So once this happens, a large amount of energy is increased, is released. So whenever you are drawing this, you always draw it as with a bigger arrow. When you are answering a question or drawing a scheme like this, let the arrows speak for themselves. Make a diagram, a scientific diagram, make it more logical, let the arrows speak for themselves. So if you have this idea that electron affinity is less than the ionization energy, we draw electron affinity with a small arrow. We draw the ionization energy with a bigger arrow, and it pointing upwards. Energy is in the upward direction, energy is increasing. So this is my scale. So this is how I will represent everything. And at the last step, when lithium plus and F minus has been formed, they organize themselves, and finally you have LiF solid, which is represented over here. Huge amount of energy. So biggest arrow is drawn over here, the red one that you see here. So this is how you represent the thing. Okay. So first part, lithium and fluorine. So it is gaseous state. This is this thing. Then second is this, the steps involved. We call it enthalpy of sublimation. The next one is that you are dissociating the fluorine. So making of lithium, gaseous atom of lithium, making of gaseous atom of fluorine, and then ionization energy, which is defined in gaseous state of the metal or gaseous state of anything, the gaseous atom you have to take. So you account for that. Then you draw the arrows for ionization energy and electron affinity part, which is here, electron gain enthalpy. In fact, we call it electron gain enthalpy, delta H naught. And finally, this is the lattice energy. Lattice energy. simply the lattice. So this is how you will construct. Now the assignment for you. Draw in your copies the a scheme Born-Haber cycle for magnesium oxide and show every step. Like magnesium will have two steps, like electron will be released. So electron, you have to take away the electron in two steps, so show it twice. Oxygen will gain two electrons, so show it twice. So how you will do it? And the scheme has to be very scientific. ठीक है ना? In this manner, drawing has to be like this relative idea of. So as I told you, you need to know how the electron affinity consideration doesn't give you a feasible thing. So you do not have formation of lithium fluoride simple in gaseous state unless you consider the lithium fluoride in solid, making of this crystal. So ions, creating the ions. So first thing, कैसे बनाते हैं Born-Haber cycle? Native state of the elements. Lithium is solid, fluorine is gaseous. Taken. Fluorine exists as F2 molecules. So I must first convert both of them into gaseous atoms. So lithium is solid, converting into gaseous requires solid to gas, that is sublimation. Or for fluorine, it is the energy of dissociation. So dissociation energy, F2 to F. So this is second step is dissociation energy. Enthalpy of dissociation, or you call it better, it is practically enthalpy of dissociation. This was enthalpy of sublimation. And then ionization enthalpy, electron gain enthalpy, and finally lattice energy. So all these things considered together. So the biggest arrow, सबसे बड़ा एरो कब आएगा? जब लैटिस एनर्जी आप दिखा रहे हैं. लैटिस एनर्जी का टर्म है सबसे बड़ा है, मोस्ट नेगेटिव, हाई इन मैग्नीट्यूड, and it is a release of energy, so it's shown by a negative sign, and in this sense it is a downward arrow. Okay, so energy, decrease in energy, downward arrow, increase in energy of the system. That is so practically it is possible to measure the overall enthalpy of formation. Directly you take it, measure the heat. So this heat should be equal to summation of all these steps. So now you can sum it up. If I can write this, so this delta HF must be equal. So this taking place in, we have assumed this reaction to be occurring in several steps in this cyclic manner and reaching the same state, lithium fluoride. So Hess's law is valid. So energy consumed in this cycle that we have taken, multiple steps that we have taken, should be equal to this one step that we are showing by black arrow. So delta HF naught should be equal to delta H of sublimation plus second step delta H of dissociation plus what? Delta H ionization plus what? Delta H electron gain. इलेक्ट्रॉन गेन इज अ बेटर टर्म. इलेक्ट्रॉन एफिनिटी एक अलग टर्म है जो कि अगर आप सही बुक नहीं पढ़ रहे हैं तो नहीं पता चलेगा. So electron gain and then plus the last term delta H naught lattice. So all these three positive term. Electron gain enthalpy and lattice energy are negative. So overall, the is feasible if these two negative terms are more than these positive terms. Then overall energy is negative, enthalpy is negative, energy is given out, and it will be a spontaneous process. Okay, and so this is also tells you that in all this, so enthalpy of sublimation can be experimentally determined, enthalpy of dissociation experimentally determined, it is possible. Ionization enthalpy is also possible, it is you can determine through experiments. Similarly, it is also possible to determine electron gain enthalpy, but it is the delta H lattice. The lattice enthalpy is not experimentally possible because the moment you have Li plus F minus, immediately it will be converted to so. So to calculate lithium, this thing, if all others are known, you can also calculate the delta HF directly. So delta H overall can be calculated. So to determine lattice enthalpy, you simply have to. So this was suggested by Born and Haber uh, that we can calculate the lattice enthalpy, energy released when the lattice is formed, by knowing this cycle delta HF minus the whole other terms, all these terms taken together, delta H naught sublimation plus delta H naught dissociation for the fluorine, then the ionization energy for lithium, and electron gain enthalpy. So all these terms taken together. So this is experimentally determined, can be determined, and all these things can also be individually can be determined experimentally. ठीक है? So lattice enthalpy, so lattice energy can be determined by following the Born-Haber cycle, because all other components that see in the cycle it is possible to determine all other things, and the lattice energy part that you see, this big arrow, this is something that can only be determined by this method, that is subtracting this enthalpy of formation minus all other terms. Okay. So this was a method was found. So the importance of Born-Haber cycle is that prior to that you didn't have any idea how to calculate the lattice energy, and they found a method by applying the Hess's law. They applied the Hess's law onto the formation of this crystalline lattice, from considering them starting from elemental state. Okay. And in this manner, if all other things are determined experimentally, this particular thing can be calculated by simply by following this pattern subtraction. So that is the importance of all the terms that has been shown. So lattice energy is simple subtraction of all other terms from this. Okay, so this is what so we'll continue from here onwards in the next class. Okay. So for this, for further understanding this thing, you will also need to understand this what something we call as radius ratio rules. We'll discuss that in the next class, and then further in-depth discussion on this lattice energy will continue. रजनी
हेलो सर
क्या
सर which topic
रजनीश
test in
हर
exam sir
जितना पढ़ा चुके हैं उतना आएगा. आपको इन द टेस्ट everything starting from valence shell whisper theory, valence bond theory, molecular orbital theory, कोवेलेंट बॉन्डिंग का सब कुछ, ठीक है। और आयनिक बॉन्डिंग
ओके
तो
सर,
अभी
ओके
शुरू
सर।
किया है, अभी चलेगा। ओके, ठीक है।
सर सर प्रीवियस डेट का रिकॉर्डेड क्लास अगर अपलोड कर देंगे तो अच्छा होगा।
सब तो अपलोडेड है, सब शेयर किया हुआ है, क्या बात कर रहे हो?
सर मतलब पिछले दिन का।
सारा तो शेयर किया हुआ है, तुमको मेल नहीं मिलता है? जैसे इसका नोटेशन जो आपको जो मेल गया होगा अभी लिंक का,
नहीं
उसमें
सर
सारा आपके साथ अटैचमेंट में सारा MP4 है, MP4 फाइल्स। आर
अच्छा
यू
ठीक है सर।
ऑब्जर्विंग केयरफुली? नहीं देख रहे हो तुम?
नहीं सर देखा था, मतलब केमिकल बॉन्डिंग का
MP4 फाइल्स
लास्ट।
अटैच्ड है ना, तो सारे क्लास का तो मिल गया आपको।
अच्छा सर
और जो
नहीं।
पीपीटी है, पीपीटी तो हमने भेजा हुआ है आपको सर, केमिकल बॉन्डिंग का।
हाँ सर वो मिल गया है और रिकॉर्डेड क्लास भी
हाँ,
सब सब मिल
रिकॉर्डिंग
गया
भी
है।
सारा है, क्या सबको नहीं दिख रहा है? आर यू एबल टू
हाँ
सी?
हाँ सर है।
तब
सर मेल के नीचे अटैच
वही
रहता है उसका
वही तो
फाइल।
सवाल है, तुम लोग ऑब्जर्व नहीं करते हो ठीक से, क्या साइंटिस्ट बनोगे? इतना सा ऑब्जर्वेशन
सर मेल के
व्हाट्सएप,
नीचे अटैच रहता है।
सब इतना तुमको सुविधा दे रहे हैं, सब कुछ, जितना हो सकता है सब कुछ कर दे रहे हैं, तब तुम कह रहे हो कि सर मेल अपलोड नहीं हुआ है। एक सूरज था, एक आप हैं, ये लोग हर बार यही कहते हैं अपलोड ही नहीं हुआ, अपलोड ही नहीं हुआ, जबकि सब कुछ उसी मेल में अटैचमेंट में आ रहा है। जब जैसे ही हम गूगल कैलेंडर में जाके आपको शेड्यूल करते हैं, उसके साथ साथ वो सारा पिछला अटैच हो रहा है, कि किसी का अगर एक भी मिस हुआ हो तो सब दिखेगा उसको एक बार में, ठीक है। तो जरा ध्यान दीजिए ये सब, ऑब्जर्वेशन इज
ओके
द
सर।
की। एक अच्छे साइंटिस्ट के लिए ऑब्जर्वेशन बहुत जरूरी है, वहीं से शुरुआत होता है नई खोज की। सबके अटैचमेंट में है, जैसे ही आपको मेल आता है ध्यान दीजिएगा उसमें। और
ओके
इसके
सर।
अलावा हम अलग से जो शेयर करते हैं उसका भी मेल जाता होगा, वो भी आप नेग्लेक्ट कर रहे हैं। एक गूगल कैलेंडर वाला जाता होगा, एक अलग से हम मीट रिकॉर्डिंग्स पे जाके सबका ईमेल डाल देते हैं, शेयर विथ ऑल, उसका भी एक आता होगा, लेकिन आप ध्यान नहीं देते होंगे। इन मेनी टाइम्स यू माइट बी गेटिंग 2 emails फॉर दैट। हाँ, रजनीश पटेल आपने हाथ उठाया हुआ है, बताइए।
सर जब वहां पे Li+ और F- कंबाइन किया था,
हाँ
तो वो गैसियस स्टेट से वो डायरेक्ट खुद ब खुद वो सॉलिड स्टेट में चला जाता है सर।
भाई, पॉजिटिव चार्ज है, नेगेटिव चार्ज आपस में अट्रैक्ट करेगा ना।
यस
तुम
सर।
बहुत ध्यान से सोचो, बहुत ध्यान से सोचने की जरूरत है आपको, आप हड़बड़ा रहे हैं। जैसे ही पॉजिटिव और नेगेटिव बना, तुरंत वो अब पास आना शुरू होगा, अट्रैक्ट करेगा। एक पॉजिटिव दूसरे नेगेटिव को अट्रैक्ट कर रहा है, और यहाँ पे कई सारे और ऐसे नेगेटिव चार्जेस हैं, वो भी आएंगे पास में, तो अपने आप अरेंज होना शुरू हो जाएगा ना सबका, नेचुरल टेंडेंसी होगा।
यस
सोच
सर।
के देखो, बनने के बाद वो सीधा उसमें अरेंज हो जाएगा। इसीलिए तो कह रहे हैं कि लैटिस एनर्जी डायरेक्टली, इट इज नॉट पॉसिबल टू डिटरमिन डायरेक्टली द लैटिस एनर्जी। और उसी के लिए सारा सब जो आप देख रहे हैं ना, इतनी बड़ी साइकिल और ये सब डिजाइन किया गया, कि बाकी सब चीजें हम एक्सपेरिमेंटली डिटरमिन कर सकते हैं, लेकिन ये दो चीजों को सेपरेट करना पॉसिबल नहीं है, कि हम पहले आयंस बना लें, लिथियम प्लस के 1 मोल ऑफ लिथियम प्लस आयंस, 1 मोल फ्लोराइड आयन बना लें, और अब हम इनको यहाँ से कंबाइन करते हैं और एनर्जी देते हैं, क्योंकि दीज टू थिंग्स हैपन सडन, एक साथ हो जाएगा जब भी होगा, ठीक है।
यस
या तो आप अलग से
सर।
F- बना लें, या अलग से Li+ बना लें, लेकिन जैसे ही दोनों साथ होंगे, दोनों चीजें एक साथ रिएक्ट कराएंगे, तो सब एक, वो आपको दिखेगा कि कंबाइन होके नीचे सॉलिड बन गया। सॉलिड
यस
क्यों बन
सर।
रहा है समझ रहे हो ना, कैसे सॉलिड बन रहा है? टाइट पैक्स,
यस
मतलब मैक्सिम दे आर ट्राइंग टू कम एज क्लोज एज पॉसिबल, एंड बिकॉज पॉजिटिव चार्ज अट्रैक्ट्स नेगेटिव चार्ज, so एक लिथियम प्लस के सामने बहुत, एक फ्लोराइड आया, इधर और 3 4 फ्लोराइड आयन से वो भी अट्रैक्ट होगा, वो भी पास में आएगा, लेकिन हर एक फ्लोराइड के ये भी देख रहा है कि और भी कई सारे लिथियम प्लस हैं, तो सब आपस में इकट्ठा होना शुरू होता है एक जगह पे, और एक पैटर्न इमर्ज करता है। दे ट्राई टू बी एज क्लोज एज पॉसिबल, एंड इन दिस मैनर वो जो आपने अभी देखा स्क्रीन पे, वो उस तरह का बनता चला जाता है, अपने आप होता है। सोचिए ये सब चीजें स्ट्रेच योर इमेजिनेशंस, ये बहुत जरूरी है। आई ऑलवेज टेल माई स्टूडेंट्स टू स्ट्रेच देयर इमेजिनेशन। जब आप ये इसी को तो विजुअलाइज कराने के लिए आपको किया गया है। ये सब कितना आपको सोच के इसको किया गया है कि ये सब अलग अलग है, लिथियम प्लस फ्लोरीन फ्लोराइड आयन। अब ये नेगेटिव चार्ज है, सोचो नेगेटिव चार्ज है, ये पॉजिटिव चार्ज है, तो अट्रैक्ट करेगा। एक एक को सोचोगे तो इसके साथ ये आएगा, इसके साथ ये भी आएगा, फिर इसके पीछे पीछे ये भी आएगा, सब एक साथ इस तरह से फिर अरेंज होना शुरू होगा और बन जाएगा। समझ रहे हैं?
Yes, sir. Yes, sir. Got
सो आप इंडिविजुअली ये सब चीजें कर सकते हैं। फ्लोरीन एटम से फ्लोराइड आयन बन गया, या ये सब लिथियम से लिथियम प्लस। लेकिन अगर लिथियम और फ्लोरीन साथ साथ होगा तो हमेशा आपको इन वन स्टेप यू विल गेट, मतलब आपको जो प्रैक्टिकली दिखेगा ये बन गया। आप सीधा लिथियम और फ्लोरीन को मिक्स करते हैं, आपको ये सब चीजें होता हुआ नहीं दिखता है। आप सीधा ये देखते हैं कि फ्लोरीन गैस है, लिथियम सॉलिड है, मिक्स करने के बाद एक और हमको सॉलिड मिल गया।
Yes.
And we are assuming it to be happening in multiple steps because agar if electron is going from lithium plus, then ionization energy involved. If fluorine is accepting electron affinity is involved, but you have defined that in a gaseous state. तो वहां तक अगर हम पहुंचने का रास्ता क्या होगा कि फ्लोरीन तक को हमको गैस, तो ये सब चीजें अगर हो रही हैं, होता हुआ हम इमेजिन करते हैं, तो ये सब स्टेप्स होना चाहिए यहाँ तक कि गैसियस लिथियम प्लस, लिथियम एटम गैसियस, लिथियम फ्लोरीन एटम गैसियस, और तब हम आयनाइजेशन एनर्जी और इलेक्ट्रॉन एफिनिटी का कॉन्सेप्ट लगा सकते हैं। ठीक है?
Yes, sir. Yes.
और जैसे ही लिथियम प्लस और ये बनेगा, नेचुरली दो, एक पॉजिटिव चार्ज एक नेगेटिव चार्ज है, अट्रैक्ट होना शुरू होगा, पास आते जाएंगे और अपने आप ऐसा एक पैटर्न बन जाएगा। इट विल हैपन बाय इटसेल्फ once you have 1 mole of lithium plus 1 mole of fluoride ion, or you can imagine any number of that way. अगर 10 रखोगे 100 रखे तब भी कुछ क्रिस्टल बनेगा कुछ साइज का something. So they will arrange themselves and a huge amount of energy will be released. So this is, देखो किसी को समझ में आया होगा तभी उसने पिक्चर सब बनाया होगा, और आपको समझाने के लिए इतना आसानी से मतलब सब कुछ आपके पास अवेलेबल है। तो यस, ठीक है। सो थोड़ा सोचना पड़ता है, सिर्फ किताब में देख के रट लिए ऐसा नहीं होना चाहिए। सोचिए, जितना सोचेंगे इमेजिन करेंगे उतना ही आपका लगेगा कि हाँ सही, क्योंकि कोई देख नहीं सकता है तुमको। इट्स ओनली सच थिंग विच जस्टिफाई, मतलब जो प्रैक्टिकल चीजें हम ऑब्जर्व करते हैं उसकी बेसिस पे ये सब उसको जस्टिफाई करने के लिए इस तरह का स्कीम ड्रॉ कर रहे हैं। सो दिस इज only way to determine the lattice energy through Born-Haber cycle. All other terms in the Born-Haber cycle are determined experimentally. It is possible to do that, but lattice energy has to be determined by simple calculations from that all other factors. Yes, और किसका हाथ? रजनीश पटेल, आपका हाथ ऊपर है, हाँ बोलिए।
सर मेरा ही वो क्वेश्चन था, पूछे अभी सर।
अच्छा अच्छा, पूछ लिए, हाँ चलिए, हैंड्स डाउन देन। ठीक है, एनीथिंग? ठीक है, यू ट्राई टू लर्न अबाउट जो पढ़ाया गया उसको एक बार रिवाइज कर लीजिए, सो दैट यू डू वेल इन द टेस्ट। ओके, ओके, दैट्स ऑल फॉर टुडे। कल फिर हम लोग रेडियस रेशियो रूल से डिस्कस करेंगे। विल ट्राई टू अंडरस्टैंड व्हाई दिस इज इम्पोर्टेंट व्हेन वी ट्राई। ओके,
थैंक यू सर। थैंक यू सर।
थैंक यू सर।
Thank you, sir.
Thank you.
थैंक यू सर।